じゃあ、第10回のハイセット特別セミナーを始めたいと思うんですけども、今日の講師は、エイドリアン・ルブロさんで、フランスのブルゴーニュ大学数学研究所の方なんですけども、タイトル、その講演のタイトルは、彼の専門分野の話をするのは昨日の話なので、そんな難しいというか、専門分野の話というよりは、そのポスターに書いてあるように、そのヒルベルトの第三問題という問題がありまして、多分彼ちゃんと話すと思うんですけども、みんながよく知っているその面積とか体積とかいう概念をもちろんみんな知っていると思うんですけど、その概念、微積とかね、そういうのだけ知っていると思うんだけど、それを改めてちょっと見直してみようという問題で、問題っていうか、彼説明すると、みんなが馴染んでいる面積と体積の話です。なので、英語で講演されますけど、ゆっくり話してもらう予定なんで、聞いてもらって、であとみんなレジュメを持ってると思うんで、ちょっとそれ見ながら、日本語ちょっとこういうの書いてるんで見ながら見てもらって、で終わってから60分ぐらいだと思うんですけど、質問とかあったら遠慮せずに勇気を持って質問してください。じゃあ始めてもらいます。
Thank you for the introduction. So, when I was asked by Takeshi to come here and give some kind of elementary introductory lecture to some subject for first or second year Japanese student, it was quite a problem for me because I'm not teaching German full research position, so I don't have any even real idea of what first year students know in France. So what I took as my guideline was what I knew or what I remember I did not know when I was a first year student. So I don't know if it's accurate or not. So if I'm going too fast, please slow me. If I'm going too slow, then feel free to ask for more speed. So it's not really possible to read the title. And so let's start. Theme of the lecture will be length. We won't be that much about the length of things. Area and volume. So these are very important notions. You always need to measure things, right? If you want to buy some land, then it's quite important to know which area you are buying, right? If you want to go buy milk or orange juice, you want to know which volume you are buying. Okay, so by experience, we really learn some kind of intuitive feeling of what is area and volume just by comparing things, right? But from a scientific point of view, these notions are not clear at all, and it really took a long time before we figure out what is the correct notion of area, length. So there are some reasons for this. So you have intuition coming from the real world, but the mathematical object tends to be much wider than real objects from the naive physical world. So for instance, you think you know that a curve is something one-dimensional, it has a length, etc. But a curve can fill out a whole plane region. So if you iterate this kind of procedure, you have a curve which fills space. So what can be the length of such things? Should be the area of the space, so that's a problem. Or, intuitively, if you want to measure the length of something, so you are walking along something at a certain speed, so you count the time it takes to go from one point to another, and you multiply by the speed and you know the distance. That's the idea. Okay, the speed is some kind of direction. It's a tangent vector to your trajectory. But if you iterate this kind of procedure, you find out some curve at which on which it's impossible to define any notion of speed at any of the points. Any of the points will have an angle like that. And so if you try to move along such a curve in the naive sense, your speed will necessarily be constantly zero. And so you won't be able to decide what is the length of this curve. Okay, so you buy some feed for agricultural purposes. You have a good idea of what you are buying. But suppose you buy some land on which some people come and they remove some spots, and they continue doing this. So the perimeter of the field is the same, but at the end, it's full of nothing. So if you think of area in a naive way, you have a field with fixed perimeter, but no surface at all to do agricultural things. That could be a problem. Well, same idea with volume. So say you buy some cheese as balls, and you continue making balls inside according to this kind of rule. Well, at the end, you still have something which occupies the volume of the cheese pot, but there is no cheese at all inside. So the volume is not that precisely related with the volume it occupies. So defining areas, volumes, has been an activity for, 3,000 years in mathematics. And this really grew up into a big subject. This is not my purpose today to introduce you to the formal aspects of this big subject called measure theory, but we'll try to get a hint of what can be definition of area and volume on simple shapes. So polygons and planes. And wow, the notion of area of polygon was already quite well understood by ancient Greeks. And essentially it's the correct one for polygons. And so I reviewed this. And if you try to escape the world of polygonal shapes, then you encounter problems. And part of these problems were solved in the 19th century using something you probably know, integral calculus. So I briefly indicate how it works and how these two notions are related. The full theory, the full measure theory really starts here at some point after Riemann's theory. So I say no. And then, since we plan to speak about volume, we go to polyhedra. So, and here I will show you two things: Hilbert's third problem and then theorem. Maybe if I have time, I'll give you a proof of this theorem, which really demonstrate that the intuitive notion, which was good for polygons, is no longer valid for polyhedra. Any questions so far? So, what do we want as properties for a theory of area of shapes? So, wow, we want that pointer or some kind of segment have no area. From a mathematical point of view, a straight line has no area. And if I take the union of two polygons which have nothing to do with each other, meaning side in two different places, a disjoint union, well, I want their area to, the area of the union to be the union of the area, the sum of the area. Okay, and I can take into account my first action. If I have two polygons which intersect along an edge or at a vertex, then I can sum their area because they intersect along something which by my first decision should have area 0. The 1 should be A. So, and we want to do something else. I have my polygon here, I translate it there, and I want to measure its area after the translation. It should be divided by that. Or I rotate it on the table. It shouldn't change the area. But if I try to make a dilatation, I inflate my polygon, then obviously it should change the area. So not all transformations are supposed to preserve area. So only for us, rotations and translation are by design area preserved. That's a built-in property of action. Okay, and wow, if I want to measure things, I have to be able to compare with a fixed information. Right? If you want to know the length of something, you have to decide what is the length of a meter and keep a meter to compare to your standard meter. So that's the normalization thing. But here it could be anything. I decide that if I take a rectangle, one edge has length 1 and the other edge has length something, then the area is just the length of the edge, the other edge. I'm telling you that the area of a rectangle has to be the product of the lengths of the edges. But I normalize one edge. And provided I know what length is, I can really normalize area this way. Okay? Okay. So, this formalism was not really formalized, but it was already known by engineers. So, three centuries before Arrow. We knew how to compute arrays. So, that's the idea. I take a rectangle with two edges of length A and B, and I declare that the area of the rectangle is the product of the length of the edges. Standard definition. It's compatible with my normalization stuff. Okay. Nothing new. You know this, you learn that. Then I take any polygon, and how do I define its area in an abstract way? So I take my polygon and I cut it with scissors, right, into smaller polygons. And then I shuffle these polygons by rotations, translation, and I try to build up a rectangle. Well, if I can manage to find some kind of decomposition, some kind of shuffling and reassembling so that I get a rectangle, then I already know what the area of rectangle is, so I can define the area of my application. Okay? So, but it's by design that it will satisfy the actions, because shuffling here is rotating, translating, etc. And I basically assuming in the definition that the area of my polygon is the sum of the area of the smaller polygonal pieces, and the same true after reassembling them into rectangle. Okay. So you know this kind of games, diagrams. So I have polygonal pieces and I make nice shapes. So with this definition, it's possible all these shapes can be shuffled back to this rectangle, the square. So all these shapes have the same area by my definition. define the area, by definition, I need to find a decomposition which can be reassembled into a rectangle. So it's not clear that you can define the area for every shape. You need to assume you can find a decomposition. So we can compute, we can check that triangles have an area defined in this sense. Okay, I start with my triangle. It's here. I cut it here. I put this guy here after a rotation, and what I get is a parallelogram. And then I can cut my parallelogram, which guy is translated here, to get a rectangle. So I used the operation I could use. I found a decomposition of a triangle which can be reassembled into a rectangle. So triangles have a well-defined area. But you can do more. Once you know they have a well-defined area, you can compute it. And guess what? It's the standard formula. 1/2 of the length of the base times the length of the line. Why? Okay. I want to compute the area of this. I know that each piece has a well-defined area. And by my action, the area of this union of two shapes is the sum of the areas. And here I took a height, so I have a rectangle. Now, if I symmetrize my rectangle triangle, I get a rectangle. And by definition, this guy can be decomposed in two pieces which will have the same area as this one. So, and here I cut my base into two smaller parts. The base at length A. I got A prime and A second. So, if I use my formula, my normalization formula, the area of this guy is A second times H. And here I have A prime times H. And this gives me the expected answer. But somehow it's a proof using the actions. And it was implicit in Euclid's definition that area of shapes was defined by using this kind of actions. Okay. Are you all right? In fact, every polygon can be given an array. So the first thing to check is that you can decompose every polygon into a union of triangles. So for nice polygons, you just have to take a random point and draw a triangle by joining a random point to vertices. Relatively clever. For this non-convex stuff, you use lines with different slopes, which are not parallel set to the edges of the polygon. And then you get some kind of either triangles or trapezoids. And then you can imagine how to cut these trapezoids. Okay, and you can even assume that your triangle have small numbers. Okay, fine. Okay. Now we have to do something to check that this theory is well built. If you're not familiar with certain mathematical term, instead of listening to me, you can try to solve it for them. So you have 4 pieces, and the puzzle is to make a square in these pieces. Okay. I'm going to talk about scissor equivalence, which is a way to formalize this idea of cutting polygons and shoving them and reassembling them. So that the formal, in some sense, definition of cutting a polygon into smaller polygons. I have a infinite polygon, I have a union of smaller polygons. The union is the initial polygon and my small polygons intersect each other only along the boundaries. So I'm putting myself in the position of playing with my actions. Because I know by design that if I take the union of two smaller polygons in a decomposition, then the area of their union will be the sum of their area, because they only intersect with the boundary. And now I call two polygons scissor equivalent if I can find polygonal decompositions of the first one and the other one, such that a pi is a qj up to rotation. So it just slightly more mathematical reformulation of Euclid's rough definition. So this is an equivalence relation. Well, if you know about what is an equivalence relation, it will make sense for you. If you don't know that, you read the definitions. If I have one polygon scissor equivalent to another one, and this other one is itself scissor equivalent to a third one, and I ask that the first one is scissor equivalent to the third one. Okay, that's a proof. So clearly P is scissor equivalent to Q, and Q is scissor equivalent to F. Now I can take a common subdecomposition in the middle, right? So I have to cut here this piece. I take intersection of the decomposition. Well, and then I throw this subdecomposition back to P and L, and I get a decomposition of P, which can be reassembled. Fine. And as the title of the slide suggests, the area in the sense of Berkeley is only the scissor equivalent class of an object. But this requires a proof. So by definition, if I have a polygon, it has an area in the sense of Euclid, and if I have two scissor equivalent polygons, then by using Euclid's definition, they must have the same area. And the point is the converse. In some sense, it's not all clear that if you take two rectangles with the same area, then they can be decomposed one into another. This requires really a proof. It's not clear by design. So, that's the statement of this theorem. You can decompose one polygon into another by transformation we indicated, if and only if they have the same area. So, really the area depends only on the class of the decomposition. So that's sketch of proof. So we already saw that we can decompose every polygon into a union of triangle, and that triangle can be decomposed and reassembled into rectangles. So we only need to check, as I said, that every two rectangles with the same area can be decomposed one into another, or which is the same, introducing an intermediate object. That every rectangle is scissor equivalent, so can be decomposed and recomposed into a square with the same area. And well, that's somehow cheating proof. That's the idea. So it proves something, except that, and I won't do it, you have to worry about what X is. In this form, the argument is taken from some article from the beginning of the 19th century. But if you look more carefully at the argument, this proof was certainly known to Euclid himself, even if it wasn't written. and probably to ancient Chinese mathematicians. Once again is just tell you the idea how you decompose the argument. If you start with a rectangle, you can cut it by the middle and reassemble it in such a way that one edge will have, such that after repeating this procedure, one edge will have length at least 1 and the other at most 1. And then you decompose this rectangle so that you can reassemble it into a certain parallelogram, which in turn can be redecomposed into another rectangle with the property that one edge of this rectangle has length 1 and the other some length. So that's where these inside pieces come from. Instead of directly proving that you can go this way to a square, this requires some formula to determine x and b. You have a purely geometric proof of this. But instead of going to a square, you go to a rectangle with one edge. That's a proof you can probably find in the literature. And it was certainly known to ancient Greeks themselves. Okay. So, yeah. I just told you this is a different argument to prove from this theorem. So, I can decompose, recompose every polygon into a rectangle, having one edge of length 1 and the other equal by definition to the area of the polygon. So we cover the fact that once we know what length is, we can use it to define area. So these concepts are really linked. And if you are more a mathematician, I have an equivalence relation on the set of polygons. That's my Scissor equivalence relation. Two polygons are sort of equivalent if they can be decomposed, and then the area is exactly the equivalent. The area of the polygon is exactly its equivalence class under this equivalence relation. So that's a formal way of defining ancient Greek area. I have a well-defined function which, as you said, to a polygon, its equivalence class modulo Scissor equivalence. And I can represent every element in the Scissor equivalence class by a rectangle having one edge of length 1 and the other one certain length. So these equivalence classes are really injections in this set of grid by length of the other edge. And this is really the area function. Kind of fancier, more fancy mathematical. Okay, questions? You feel comfortable with ancient Greek area? Hope so. Okay, here's another way to find area, and you are certainly familiar with this. So we draw a polygon or shape on a graph paper, and we count the number of squares inside it. And so this gives an intuitive lower bound on the area. The area of the guy is certainly bigger than the sum of the area. Now I can count squares which contains at least a part in the figure. So that's some kind of external area. And I just realize that there is one square missing here. So anyway, this gives an upper bound for the area. And okay, so if we are already happy with this approximation, we can declare that the area of this region, which simply looks like Australia, right, is something between 31 and 64 square. and well, could be inner. If I'm not happy with that, then I take a graph paper with smaller squares, and I count again. And what I get is some kind of better approximation of the area inside and the outside area. And yeah, we hope that when we take smaller graph papers, these two approximations will converge to a same number. And if so, we say this number is the area. And most likely, you were told that's cool that the area of the shape is something you can imagine that these two approximations will go to the same thing and define the area. But that's clearly a hope for the moment. You have to prove that this inner and outer approximation converge to the same thing. So, if so, this is the area. This is really intuitive, and it was already used again by ancient Greeks. If you want to compute the area of a disk, well, a disk is not a polygon. So you don't have any Euclid area definition, but you can approximate a disk by regular polygons inside it. And the more edges you put, the closer to the disk it gets. So at the limit, you should get the area of the disk. And that was Archimedes' idea, and he really gave a proof that the area of the disk of radius r should be pi r squared. But he had absolutely no definition of limits, convergence, this kind of thing. So it was some kind of intuitive proof. So if you want to formalize this, you need really the tools from real analysis. What does it mean to have a limit? What does it mean to converge for a sequence of some kind of other objects? And these things were really formalized in the late 18th century and beginning of 20th century. So the theorem is here. If you take a polygon in the plane, then I really have a notion of area. The inner area and the outer area approximation will converge to the same number. So that's the G area of P. Notice that Euclid's area was not gamma area, gamma is for Greek, and G area, that's German G because Riemann was German. So, and the function we get, which associated to a polygon, its area defined as the limit of approximation, really satisfies the actions we expect. So, and I won't prove anything here. I just give an example. That's a difficult theory. Really. So let's check at least that it satisfies this action. So areas of lines and points in this sense are actually zero. I want the inner area or inner approximation of a point or of a line should be zero. So that's by design. Area of rectangles are normalized. I mean, I define things through graph paper, so I have areas of rectangle as I do. Now, if I rotate my graph paper, I really change the number of square I can see in a shape or contain in a shape. So for approximation, rotating or translating might influence the process. But when we go to the limit, taking smaller and smaller squares, well, this has no influence. I mean, I rotate my shape, and inside, if I take a smaller graph paper, I can count smaller rectangles inside the rotated big ones. So no problem. But it's a limit argument. It's really related with the fact that we converge to something. And additivity with respect to polygonal decomposition, which was part of my requirement for a theory. So if I look at the squares contained in a piece of a polygonal decomposition, so inside a piece, or they are certainly inside the whole polygon. Okay. So is it clear for you? So suppose I take a position at a random. So I'm counting square inside each piece of the decomposition. So the condition is that they must be really contained inside the piece. But if they are contained inside one of the pieces, they are contained in the polygon. So this gives me that the lower bound for the area of P, the number of polygons inside, is bigger than the sum. Because this box is inside P, but it's not inside any of the pieces. Well, and you can imagine, so this implies that the area of P is at least equal to some areas. And if I have a square which contains a part of P, this one, well, it certainly contains a part of some Pi. Okay? But there are overlaps. Right? This square contains a part of P, but it contains a part of this guy and the other guy. So this guy will be counted twice if I take the union, but it will only count one if I take the value, well, if I consider P itself. So this really means that the upper bound I get for the area of P using these boxes is smaller than the sum. Because in the sum of the upper bounds, for the pieces, this guy is counted twice. But for P, I only count it once. Okay? Well, this gives me the other inequalities. So it satisfies my functions. Okay? Let's go for an example. What is the area of a triangle? I define it using this theorem. Well, it is the same as the Greek arrow. 1/2 of the length of the Greek arrow. So the two notions are compatible, but this really requires a proof, and not a geometric proof. No, we have to compute using approximations. That's something you probably did. So I take my triangle, it has height h, and I won't cover it with small boxes. I will cover it with strips. I do think in one, I eliminate one step. I should cover each strip with small boxes. So the area of the big strip at height z is this, because you know that the length a prime of z by Thales' theorem, for instance, is the ratio finite. Okay. So, and so I will cover my triangle with a certain number of big strips of 8 dz, and I will need ground floor of H divided by dz, where dz is to cover the shape. So the area, the upper bound for the area, since I'm counting more than what I should, is, so the area is smaller than this, and I use my formula. Then I'm summing from 0 to round of H divided by dz, so I know what it is. I mean, this is an integer. You know this notation? Yeah? No? Not familiar for you. Okay, so I have H, and I write H is k dz plus r, where k here is an integer, and this guy is pretty smaller than this. I'm counting how many integer times I have dz in my H. If all these guys were integer, this would just be Euclidean division with the so so k is what I denote by. Okay. The number of time I can put dz in H, except that I have some less. So now it's just the formula of the first, the n first integers. And well, now I let dz go to 0. This is the same as saying I'm taking smaller and smaller boxes, right? So this behaves like H divided by dz squared, right? I multiply by dz squared, so it should converge to 1/2. Okay? Are you all right? Okay, now I do the same with the small strip. Little trickier because the small strip, the area of the small strip depends on what is that I add z plus dz. So written like this. Now, since I'm looking at smaller strip, the area of the shape should be bigger than the sum of areas of all smaller strips. I do some computation. So I find the same thing as before, plus some term coming from plus dz stuff here. But I don't care because this term behaves like dz squared over h. And when dz, when the height strips goes to 0. So, if you did some calculus, it should remind you some. That's the definition of Riemann integral. We are computing. Okay, we are forget about this. Draw a big line and look at a function whose graph will be that and that. I'm computing the area below the graph of the function. And if you learn about Riemann integral, that's what Riemann integral does for you. So that's this definition of volume of area is really the same as the definition of Riemann integral. So if you know how to compute integrals, you know how to compute the area of many shapes, not only polygons. Yeah, here it looks like a triangle, but if I take the graph of a reasonable function, a function for which I know it has a primitive or it has an integral, then I can define the area below the shape as being the integral of the function. And so Riemann definition is much more flexible. It applies to any reasonable shape whose boundary would be given by a reasonable curve. curve which locally looks like the graph of a Riemann integral function. So it's much more general. But for polygons, a priori, I have two different notions. I have Euclid's notion, and now I have this Riemann integral area notion. The good point is that the two notions coincide, and we already saw the proof. These two notions coincide for triangle. We computed Euclid area of triangles, and we just did the computation for our newly defined area function. And we saw before that every polygon can be decomposed into a collection of triangles. And my two functions satisfy the same actions, right? That I'm computing area of unions of polygons by just summing areas. So they coincide on basic object, and they satisfy the same action. So, all right. And this really means that two polygons have the same area in Riemann sense, in Cauchy Riemann sense, if and only if they can be decomposed by cutting polygons. But it was not at all clear from the beginning. It was a built-in property of Euclid's definition. Here it's somehow a theorem for this Riemann notion. Okay, so, and can we do the same for volume, polyhedra states? So polyhedra, by the way, these are compact shapes which are made by gluing polygons along edges. Polyhedron by design is something which is closed. It's not going to infinity, it's not open. I mean, a ball is not a polyhedron. That's not closed. Let's try to see what we expect for theory of volume for polyhedrons. So, the volume of a point on the curve has to be 0. And the volume of a surface has to be 0 too. I mean, we want to compute something which is, we want to consider objects that are not fit. Now, if I have two polyhedra and either they don't intersect or they intersect along their boundaries, so faces, edges, vertices, then the volume has to be the sum of the respective. I mean, if they don't intersect, that's natural, and if they intersect each other along points, curves, or surfaces, we already took care of. Okay, and the volume should be again invariant under elementary operations, so rotations and translation. If I put coffee in my cup and I go from here to here, I mean, the quantity of coffee inside should remain the same. For rotation, it's not that clear that the amount of coffee will stay the same, but okay, you get the idea. And we normalize Hooke's theory. We need some standard volume to compare with. And so I say that if I take a rectangular box of height 1, then its volume is equal to the area of this case. So I'm saying that if I take a rectangular box, I want its volume to be equal to the product of the lengths of its edges. That's equivalent because area was normalized. That areas of boxes are product of lengths of edges. Okay, so we can really try to adapt this Cauchy an idea to define volume by successive approximation. So I start with a polyhedra, and I try to fill in as many boxes of a known volume inside. Okay. One thing is Q. The global thing is the shape, and I put small boxes of known volume inside. And I count, I sum volumes of these boxes, and I get my logo. Now I have my object. I can try to take a big box and put it inside my big box. So this, if I know the volume of my big box, I have an upper bound for the volume. So that's the idea. If you try to enclose your polyhedron in a union of boxes of volume, you have an upper bound. That's exactly the same idea as for parallels. So upper bound, and now we take smaller and smaller boxes. If I try to put the box in some shape, there are some room left inside the box. So I take small boxes and try to read and see how much boxes I say can put in the room. Measure of the volume. Okay, and same thing. Hopefully, we converge to some of these two approximations, given by volume of boxes, will converge to some number that we define the volume of the solid. Similarly as for areas, it's not clear at all that this quantity really converge in general. But luckily, this is true for polyhedra. So you have a nicely defined theory of volume of polyhedra, and the axioms for theory of volume are satisfied. So I won't do again the second part because it's exactly the same as what we did for area, and I won't prove the first part because that's a difficult theory. But the idea is essentially the same. We approximate and try to prove that the lower and upper approximation are convergent to a solution. We did it for the triangle. You can do exactly the same thing for the tetrahedron or a pyramid. So the tetrahedron is something like this. Let's see. Okay, that's a tetrahedron. It has some height h, and I want to compute its volume by this idea of putting boxes inside and inside. So what I do is that instead of a strip, I look at some kind of slice here. And these slides will have height dz, it will sit as a certain height z, and provided I can compute the volume of this guy, I'll do the same Riemann integral trick, and I find out the volume of the tetrahedron. But, okay, by what we already know, so I should a priori find the volume of this inside strip, but this is not a box. So first, try to approximate it by a box like this. So I take interference, and, okay, but still it's not a box. It really looks like that. But, well, I can decompose the base of this box, which is a triangle, into a finite union of rectangle, for instance. So I can decompose this shape into boxes. So it's fine. I know already how to compute from what we did for area. The volume of this guy is just the area of the space multiplied by its area. So the problem is I need to know the area. But I'm playing in a triangle, so once I know length of edges, I can recover area of this Thales theorem again. So I know how to compute the volume of this guy, and I take the same summation and check everything. So, and I find standard form. So that's exactly the same proof as for the triangle. Now, you can adapt the notion of Scissor equivalence to polyhedra. I mean, we want to cut polyhedra into smaller polyhedral pieces and try to reassemble these smaller polyhedral pieces into other polyhedra. So, so polyhedral decomposition is precisely what I said. So it's a way of cutting polyhedra into smaller polyhedra, which equals polyhedra. So there are two illustrations of a polyhedral, two possible polyhedral decomposition. And now Scissor equivalence translates this way. So you can imagine you no longer use scissors to cut through polyhedrons, so you need a saw. It should be called chainsaw equivalence or something like this, but it's dissection. Cut solids. So there are dissection equivalent if and only if there can be decomposed into smaller polyhedra which can be reassembled to form the and you just saw some way to position and to reassemble. Okay. So by my actions for you, I know that two dissection equivalent polyhedra will have the same volume. I said in the theorem that my notion of volume satisfies the action. And inside the action, there is a built-in thing that you want it to be compatible with this kind of position. And, well, let's ask this question. So, it's a converse. Suppose I have two polyhedra with the same volume. Can I dissect one into the other? So for polygons, we checked it was true that polygons with the same area can be decomposed one into another. And so this is not just a question, this is a famous problem called Hilbert's third problem. And this problem was asked by David Hilbert, a German mathematician at the beginning of the 20th century, during a very famous lecture at some international congress of mathematics. And he not only asked this problem, at least my guess he asked for two other problems, but he posed 23 problems. And so some of them are solved, and some others are still very, very actively researched. So, I mean, besides wearing funny hats, he was also asking very serious questions. And these questions really serve to develop modern mathematics. So, he expected the answer to this question to be negative. He expected that there exists polyhedra with the same volume, but which cannot be decomposed one into another. And indeed, a counterexample was found to 1 year after, actually, by a former student of Hilbert, which was called Max then. And what then proved is that if you start with a regular tetrahedron, you will never be able to cut it into polyhedral pieces in such a way that you can reassemble these pieces into a cube of the same group. So what we saw for polygons having the same area is equivalent to being decomposable one to another. Really fairly dramatic for polyhedra. So this means that volume is quite subtle notion of area. I don't know if I should give you an idea of proof of this theorem. It's not that difficult, but you really need some maths to do that. Maybe I can just give you a very brief sketch. And it will be even rougher than what I had in mind first. So if I take an edge of a polyhedron, it has a length. But we can attach another number to it, which is a number. I have two faces of a polyhedron. These two faces meet along an edge with a certain angle. So to each edge, I can attach a number. That's called the dihedral angle. Now, once I have this notion, I pick an additive function from R to R, and I impose that it vanishes by 0. So by additive, I mean that f maps a rational multiple of any real to a rational multiple of the image. So if you know about vector spaces, it's a q-linear function from R to R. Yes. I consider the real as being a vector space of a q, and a typical additive function will be a q-linear function from R. Now I can define, once I have such an additive function, I can define the then invariant of the polynomial with respect to the function. So I take the sum for all edges of the image of the dihedral angle multiplied by the length of the edge. I can do that. And crucial point I won't do is to check that if I take a polyhedral decomposition of P, then the then invariant of P is equal to the sum of the then invariant of P. So this means that it doesn't depend on the dissection equivalence. If I can dissect one polyhedron into another, then they should have the same then invariant. But that's an invariant which is clearly finer than the unit. So, well, let me take 1 minute to explain you how you can try to prove this crucial formula. So, so we have polyhedron, and we will take a decomposition into smaller form. So let's suppose that inside my decomposition, I'm creating some new polyhedron which has an edge which is entirely contained into the initial polyhedron. Then well, my decomposition should look something like this, for instance. So the dihedral angle I I see around this particular edge merge sum to 2 pi. If I look in the direction of the edge, I have to see something like that. That's my edge E here. And these are the faces between L and E. If I take a decomposition such that one edge is entirely contained in P, then my decomposition should look like that. So that's one dihedral angle I see, say, by taking for P1. This would be P2, P3, P4. So in the sum here, I see the sum of the dihedral angles there. But this sum is equal to 2 pi. And I take f of it. So, and f is an additive function. F of pi is equal to 0, so f of 2 pi has to be 0. So, edges in the decomposition, which are entirely contained in the shape, will play no role in the formula. Where you have some terms here, but they get multiplied by 0. Okay? For the possibility, one of the edge which appear in the decomposition is like this. For instance, I need to go like that. So I see two polygons here. And since this edge is contained in the face of the polygon, if I look at the sum of dihedral angle, I see around this edge, this sum must be pi. It's contained in the face. So if my edge is here, I have no choice. The other two guys, whatever I do here, the sum of the angle. But f pi is equal to 0. So this term plays no role in the then environment when I change to another decomposition. They just add 0 terms everywhere. Now, and the final thing is, if I take, well, if what I'm doing is decomposing an edge itself, say, like this. Well, the part taking into account the dihedral angle won't change, but I will just subdivide lengths, the length. I will just subdivide the edge into smaller ones. So in the left-hand sum, I see the full edge, and in the right-hand sum, I see the sum of lengths of small edges, but these sum of lengths are precise. That's essentially the idea. Oops. So, and now conclude. So, if I take a regular tetrahedron with edges of length 1, so I don't care about the length of edges. So the regular like this again. So I see 6 edges, and since this is a regular tetrahedron, so all faces are equilateral triangles. So all the dihedral angles will be the same. So this phi is the dihedral angle you see between any pair of faces, and there are 6 edges of x1. So that's the then invariant of my regular tetrahedron. So, well, the then invariant of a cube or any rectangle is 0. Why? I take a cube, and guess what? In the cube, the dihedral angle are all equal to pi over 2. But f of pi over 2 is 1/2 of f of pi because I chose an additive function. And so it is 0. So I'm just summing zeros there. Okay. That's the last tricky part, but it's more real analysis. Well, I mean, that's a computation you could do in high school. Compute this dihedral angle. It's the arc cosine of 1/3. It's just playing with angles in the triangle. So normal vectors of faces, what? And a little more trickier. The ratio phi over pi is not a rational number. You can use trigonometric formulas to compute this. So this implies that, and that's a deeper thing, but it has nothing to do with the geometric problem. You can really find an additive function, f naught, so that f naught of phi is equal to 1 and f naught of pi of 0 is equal to 0. The reason is that if you know something about vector spaces, you view R as a vector space of a Q. That's, as a vector space, it's infinite dimensional. And if you take a rational number and an irrational number, will certainly form a family of two independent vectors. I mean, there is no linear combination of a rational and an irrational that can be 0 unless the coefficients are 0. For otherwise, my irrational will be rational. So I take phi over pi and pi over pi, which is 1, as a free family in R as a vector space of Q. I complete this into a basis of R over Q, and I define a function on my basis, and I declare that f of phi over pi will be 1 up to a translation. So mixed thing. But the idea is that phi over pi is not rational, and pi over pi is 1. So they are independent of Q, and I can cook up some additive functions. That's linear algebra. So I take this F0, and so the then invariant of the tetrahedron computed with F0 is equal to 6. While, as we said before, the then invariant of any cube with respect to the function has to be equal to 0. Okay. So you cannot just decide by looking at volume if you can decompose one polyhedra into smaller pieces and reassemble them. So really, there is no Greek way of defining volume. You cannot play with finite decomposition into smaller volumes. You really need this kind of integral form, this kind of limits of approximation to define volumes compared to areas. But in fact, you could decompose this tetrahedron into non-polyhedral pieces, which can be reassembled to a cube. Well, you can try to do that. This is possible if you allow yourself non-polyhedral pieces. But actually, something very strange. If you take a ball, unit ball in L3, there exists a finite decomposition into certainly non-polyhedral pieces, so that if you make this decomposition and try to reassemble things, you obtain 2 unit balls. So I solved double the volume by taking a decomposition. This means that the notion of volume I gave you using this approximation, this Riemann approximation stuff, is not well suited. The pieces cannot have any well-defined notion of volume, because otherwise it should be preserved by such kind of composition. So in some sense, the finitely many pieces have no volume at all. It's not that they have volume zero. They exist. I mean, the problem is that you will never be able to define the volume of such pieces. So, that's illustration of this paradox I stole from Wikipedia, but that's a big limitation. Whatever you do, there are objects to which you can't assign any reasonable notion of volume. The same was essentially true for the first object I showed you, this curve filling the space, or these credit sponges, surface full of holes, etc. If you want to define the area of such guy, it has to be zero in any sense. And here, if you want to decompose something into twice, you have to cut it into pieces which have no volume at all. So there is no effective way to do this. I mean, that's some kind of existence theorem. That's an abstract statement using the theory. It's not a contradiction to the theory. It says just that you can find a decomposition. It's not giving you any algorithm to produce this decomposition. So it's not a physical world paradox. It's not even a paradoxal with respect to the theory. The theory allows this. You can decompose things into another, but if you don't keep the notion of volume in the middle, you shouldn't be surprised that at the end, when you reassemble things, the volume changed. In the middle pieces, there is no notion of volume. So it's not about taking a knife and trying to do this decomposition. If you try to cut something with a knife, you can attach notion. So it's some abstract form, existence theorem.
その面積の定義の仕方がみんなが知ってる微積でもできるし、こういう限界の操作に切っていってこう集めて要は長方形のやつの集まりに戻すっていうその二通りの方法でできる。だけど体積の場合にそれができるのかっていうのが彼が説明してもらったルベルトの第三問題で、みんなが知ってるようにどんなそのポリヘドラという多角形のインテグレーション微積分を使えば計算できる。だけど面積の時みたいにそれを基本的な形にカットしていってすることができる有限界の操作。微積っていうと無限界の操作になっちゃうからダメなんだけど、有限界の操作でカットしてできるかっていう問題のルベルトの第三問題なんだけど、彼が説明してくれたみたいにそれができないっていうのが1900年からに承認される。そういう話をしてもらったんだけど、
Final decomposition? No. What?
And this is all
Do you know about the action of choice? I mean, okay, let me tell you, is it natural for you that if I take an infinite set, I can decide to pick infinite elements inside the set? Do you consider it as normal?
You can run a supercomputer that can.
No, well, that's infinite stuff. So even, well, I mean, every supercomputer will work in finite stuff. That's, there is some high infinity hidden behind. There are finitely many pieces, but the formal existence theorem of the decomposition involves some infinity state. The fact that you can, in an infinite set, pick infinitely many elements. And this is some kind of action of mathematics that you can do that. And from this kind of formal action, you deduce formal existence.
Even if it's a regular object as a regular trade, so for a cube or a...
Well, if you want to, if we are not speaking about this Banach-Tarski phenomenon, if you want to decompose one shape into another by things which have volume, yes, you can try to ask a computer. But you see, finding all polyhedral decomposition of a given polyhedron, you won't be able to do that. Again, it's some kind of continuity problem. I mean, objects are not discrete. You can add as many edges as you want, and you have no guarantee of how many, on the number of pieces you need to look at the decomposition. So if you are lucky in finite time, finite reasonable time, you get it. You know, if you know there is a finite decomposition, you have a chance to find it, but there is no good estimate on the number of pieces, maximum number of pieces. You see the problem?
I understand the problem.
It's a time problem.
But for a volume,
Yeah.
for any given volume is infinite because you can.
Yeah, well.
decompose it. But only just try it as an experiment, just like for fun. Give a pyramid to a. Let's
Yeah.
take this pyramid to a cube.
Yeah.
And show it to a computer and see if it can solve it. If it can solve it, it can maybe glance something about, oh yeah, maybe we're doing something wrong.
Well, if you can solve it, well, the thing is, you can't solve it by this theorem, right? If you take a cube and the tetrahedron of the same from you won't find any decomposition by polyhedra. But you could find decomposition by other shapes. But how do you implement that?
I don't know, I'm just asking if you don't try, or is someone trying to?
Well, I mean, as mathematicians, we are happy, right? You have formal statements, theorems, saying this you can do, this you can't. Then if you are doing applied mathematics, certainly you are interested in a question like, how many times does it take to do that? Well, as pure mathematician, I never tried to do that. I mean, it is possible, it's not possible, the rest.
But I heard that the problem of the four colors was solved with the use of materials.
Okay, for problem of four colors, you have first some kind of formal abstract reduction to a finite number of cases, which can be checked in finite time by a computer. So you can't get rid of some part with abstract argument. Once you reduce a problem to a finite one, I mean, involving checking finitely many cases which can be checked in finite time, then okay, you can use a computer. But some problems cannot be reduced to finite ones. So a Kepler problem, same thing. What is the perfect shapes to buy oranges, for instance? Well, that's the one you imagine, that's the one you see to come up, proof for that. And you reduce the problem to checking that a finite number of configuration at the appropriate properties. And then you put it into a computer because you no longer see any formal proof that you can improve the discussion. You check by hand, you check by computer at the end when you reduce finding cases.
有限文芸の数学ではいろんな問題があって有限でできる場合だとコンピューターにバカッと計算するやつだけども、例えば今日の話の不可能な数学者も性質として具体的に計算するというよりはそれが可能か不可能かというのを知るのが、応用数学者は別かもしれないですけど、工学部の人ですね。けども数学者としてはできるのかできないのか、それが今日の話があって、そういう時には、パソコンどんだけ計算しても結局は例えば今日の問題とか無限界の操作とかでは限界があるので。有限界の操作があるんだけど、そういう有限界の操作で終わる話だったら、そこは全然使えないけども、例えば今日の最後の方のエレベートの第3問題の証明の概念とか、そういうパソコンと全然必要ない。あれはもうだから、すごくキュービックと、少し締めたいが、同じ体積でも切ってできないけど、うまいこと。導入してそれが一致しないというのを言っているんだけども、そういう感じで分解できないという分解できない互いに付き合わないという可能か不可能かというのに数学者というのは結構関心があるというのが分かってもらえたらいいかな。もちろん彼が言ってた4色問題とかそういう有限の話だったらパソコン使ってできるんだけども、今日の問題というのはそういうわけで他にもまた時間があったら時間使うのか何でも、今日の話に関係なくてもいいかもしれないけど、何かあったら成績つけるにはどうしたらいいですか？
レポートを今持ってますので、ちょっと頭の中で整理していただいて、1分ぐらいしたら整理します。
どうするんですか？ちょっと待って。その間なんか質問今日の内容というのが説明してたけども、1900年に出てたヒルベルトの問題で、言ってたけども、いまだに解かれてない問題が23問題があって、そのうちのどんな解かれたか知らないけど、ある程度解かれてるんだけど、実世紀以上だって解かれてない問題があるんだけど、今日の話したヒルベルトの第3問題は、提唱された2年後に解かれたやつですね。割とヒルベルトのお姉さんで解かれた。割と、簡単ではないですね。興味ある人とかは、ヒルベルトの問題などを聞いたら。
ということで、出席したということの代わりという意味でもレポートを書いていただいたので、ただし極めてミニマムなということで、どんなことを書いてもらっても構わないというのが立場なんだけど、でもせっかくキーワードで出てきてるから、ヒルベルトの第3問少なくともそれはどういう問題なのかということを理解してもらうというか、という意味では書いてもらう。最初は4色問題の話ですか？そう言いなかったの。
いや、そうです。
でも4色問題っていうのがあるんであれば、それについて書いてもらうし、他の何かしらわけわかんないような問題というのは数学の世界もありそうな気がしてますが、23分かけ方だから、それについて課題として出してもらうと思います。ないしはそれを調べるのも、こんがらがるチームだったらば今日の感想でもいいということで、あんまり分量多くなくて構いませんから、今日の取りまとめということで出席があるのにとして、例の Gmail のアドレスって言ったら分かりますよね。あそこのところに、期限設けなくてもいいんだと思うんだけども、一応目安としては2週間ぐらいの間に出してもらえますかね。 っていう感じにしました。
なので、まあ、お任せしていいですよ。
あとの評価は、それをどういうふうに使うかは。
わかりました。
じゃあいいですか。
はい。
じゃあ写真撮ってみますか。皆さんよろしいですか。はい。じゃあいつもだったらこっちからこういうふうに撮るんだけど、今日はこっち側にみんな無理に言わないで体を動かして次に来てもらって、でそこでの間作る。